Okay, we're recording. I can trim this out.
Yeah, so our milestone 3 right now.
For the camera, make sure you state your names.
Okay, I'm Joe Pizzamenti.
I'm James Love.
Sean Trimper. Yeah, so right now we took milestone 3 out just because we have a first order filter running into a second order filter. And then our voltage is dropping way too much to be able to drive our servo motor.
We found that it's not what we wanted to do. That's
First, let's go over the scope of the course.
Yeah.
The scope of the project.
Yeah, so right now we have the rest of it working. So when you guys want to demonstrate, we have 2.
Well, okay, so we have a sun follower.
Yeah.
So the point of this is to have a bunch of solar panels that we have in this box right here. Haven't implemented it yet. But we have a bunch of solar panels that we got from Jason Anthony. And we're going to, he was from his backyard garden. And we're going to throw it on a plexiglass sheet and then have that sheet attached to a servo or a stepper motor that is capable of following the sun so that it's working as efficiently as possible. And from there, we did that by taking 2 photodiodes, finding a difference in voltage, and running a bunch of op-amp math, sending that into a 555 timer. From there, to generate a PWM signal for the motor to see which way it needs to turn, how fast it needs to turn, all of that. And then milestone 3 was supposed to be to filter out that signal so that anything above 3 kilohertz and below 10 hertz wouldn't damage the motor.
Okay.
And that's just the general idea of what we've made.
Okay. Yep.
Okay. Should we run through the simulation or not yet?
Do you have a high-level block diagram?
Yes. Okay.
Okay.
Yep.
or actually, I could just open it.
I pretty much heard it in what you said. But
Yeah. No, that was the op-amp math. More specifically, it goes from what's it called? Inverting op-amps on one of them, and then the other one stays the same, and then it sums them together to take a difference.
So, sun, light, 2 photoresistors, got it. Op-amp math, okay, what you're talking about right now. One of them is an integrated effect. Okay. You ascertain A stable to make square wave, low pass filter, right? PCP frequency stepper motors. Okay.
Yeah.
And then external power motors.
And that filter there is a third order bandpass filter.
You have a third order band.
Yes, to implement both a first and second order filter.
That's going to be fun to talk about. And,
Yes.
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 Filter, of course, in solar cells, auxiliary power. Good. Very good milestone. High-level block diagram. Good.
Thank you. Okay. James, do you want to show off the LT Spice?
Okay. So,
It's a bit of a mess, but it gets the job.
it's fine. I would say this is fine.
Yeah.
Okay, so we have, first of all, these are the 2 photoresistors.
Yeah.
And then, say they're connected to a 9-volt battery, and then they go, this pulls it to ground. So this is, I think,
That's
so
our
one of
inverting
one of
op-amp.
them inverts it so that we have basically positive voltage, negative voltage. So we're subtracting this one from this one. So we get like, if it's positive voltage, then it needs to move up, and negative voltage needs to move down.
Okay.
And then those are summed together in this summer, or inverting summer technically. And then we also have this negative 9 volts going into 27 kilo ohms resistor here. What this does, it will add an additional negative 3.3 volts. So the output, instead of outputting like a center of 0 volts, it's like a center of 3.3 volts.
Okay.
So that's because for the motor, 3.3 volts is like in the center. And then like it goes down. Below that is moving one way, above that is moving the other way.
Okay.
Then we have here, if we found that if the motor, well, actually you'll see this when we demonstrate it, but if the motor is like too close to like 3.3 volts, then it doesn't move, but it kind of makes a grinding noise, like it's not supposed to be doing that.
Okay.
So we implemented something. We also realized that might waste power in the long term if you have this on like all day.
Yeah.
So we have something where if it's between 2.6 and 3.8 volts, it stops moving. So we have these which would detect either of those conditions,
Cool.
and then we put it into this. This is what we were telling you about, where we needed a transistor.
Yeah. That's great.
So if either of those are active, then it will let our signal come through. So then we have
An integrator.
integrator here. Do you want to explain that at all?
We have an integrator and then an inverter from there because it's an inverting integrator technically.
Your integrator is interesting.
So we had to throw a resistor on there to make it like a transimpedance kind of thing, because having no resistance in the feedback loop made the capacitor not act the way that we wanted it to, ideally. And we were like, oh, this actually works.
That is called a Miller integrator.
Oh, okay.
Good
Cool.
job. Good
And
job.
we just kind of invented a Miller integrator on the fly.
Yay! Welcome to learning on your own.
Yeah.
Good job.
Thank you.
Yeah.
So yeah, we have that signal then going into this 555 timer.
So this is our what's actually a stable multivibrator.
Yes.
And we found. I guess we'll talk about that later. So when this. Yeah, so this will take our constant voltage signals, which is centered around 3.3 volts, and change it into a PWM signal, because it's not actually 3.3 volts that the motor takes in. It's like even 50% duty cycle, which corresponds to 3.3 volts. So actually what the motor is doing is above 50% duty cycle going one way, below 50% duty cycle going the other way.
Okay.
And then that goes into a third order bandpass filter, which
Prevents damage to the
Yeah.
motor. That was the intended output. We'll
unfortunately,
explain that
it
later.
also reduces the voltage, which is not what we want, and then it doesn't work again.
Do you know why it reduces the voltage?
Yes. So as a third order bandpass filter, when we run the LT Spice, we found linearly it was 0.59 compared
Should I-
to 1.
Should I show the difference?
No, Sean
Yeah.
Sean will show that.
But just make sure at some point I want to see a probe of your LT Spice and what you
Okay.
expected.
Yes. Yeah.
That this helps. Wherever
Right.
you want.
Mhm. Yeah. We'll show it all.
Cool.
Okay. Can we move on to showing off the physical
Yeah,
circuit?
okay, then we'll
Sure.
talk about it.
So overall, general idea, because we're trying to figure out what the best way to have two photoresistors, photodiodes, whatever, and get it to end up going to a motor. So we're saying,
Shall I pull out the
you
sun?
put 0 volts as
Oh, you can kinda
balance,
hear it.
and then just use plus and minus to figure out your direction.
All right.
Cool.
Let me put the sun in the right place.
Where are
One
the
second.
photo? Are they photo?
Those are the two photodiodes, and depending on where the flashlight is,
Yeah.
Second.
James is our artificial sun here. You have the motor spinning in two opposite directions at a varying speed depending on the.
Okay, here. So this is
Okay.
the sun is it's like that, and then we can go this way.
Okay. Yeah. Those are indicators on the right. The LEDs.
One of them is obsolete because we had a negative voltage in our milestone one,
Okay. Then.
but one of them is, or one is integrating. Yes, it is.
Okay.
Okay, so my hand is not really stable enough to be the sun.
It is a very sensitive circuit with the
Yeah.
way we've calibrated it, but
Okay.
it works.
So now I also can't see the direction of the motor, but
It's going to the
I
right.
need a flag. Or something.
is what this was for.
Thank you. That'll help a little bit.
James,
Okay, let's.
can you stabilize it real quick?
Good luck. I have to pause this whole thing.
There.
Oh,
Okay.
yay! Thank you.
Okay.
Yep.
So here.
Yep.
And then we can go like this.
Cool.
Like this. And then for some
Goes
reason.
the other way.
It went the other way.
Yeah, the other way.
It's a bit finicky, but it works.
Yeah, I think that's because it's
Yeah. You can,
approaching the theoretical limits of some component in here.
Many components, actually.
Yeah.
We have several components.
I have questions, but that's okay. Cool. Yeah. Generally speaking, it's doing what it should.
Yeah.
Yep. Oh yeah.
Okay. So I'll just explain really quick.
Yep.
everything op amp is here. Those are the two photodiodes. Take the difference. The indicator LEDs, which I'll show here, which we had with the NPN.
Yeah.
We did not implement it because it implemented some current draw issues. It was like we weren't really sure why or how to work with the transistor to indicate that.
Yep.
So we just ended up scrapping that portion. Still works entirely without it. And then a part of milestone 2, which was the 555, is right there.
Okay.
We have external power from a very cheap battery bank to drive the motor.
That's because we needed 5 volts, 1 amp.
Yeah.
And,
Yeah,
these
yeah.
are neither 5 volts nor 1 amp.
We refused to use a current buffer, so we have micro USB to 5 pins.
Oh,
and it's very fun to use.
I'll take it. Okay.
And
Cool.
that would then go into this filter, which we were not capable of using as the PWM signal for the motor, because the motor wants 5 volts. We were able to get it to work with 3 volts for the PWM signal.
Okay.
If James could pull up really quickly, we just ran really quickly before class. Not the simulation, the screenshot.
Oh, right, yeah.
So we're able to.
If we actually,
Yeah.
So this is what happens when we plug that directly into our output.
we get 1.1 volt amplitude, which is not anywhere near enough because it is reduced.
Also, the motor is not supposed to accept negative voltage, so it turns out we were actually possibly damaging the motor, but it's
by trying to prevent damage, we could have damaged.
Yes.
So, the photographer's here. who is retracting? Yeah, cool. So your amplitude reduced from 5 to 1.5 or something like that.
Yes.
So why specifically does that happen?
Because we have too high of an order of a filter.
Okay, and what is the thing that causes attenuation? Mostly. Like, I want to know, do you have a Bodhi plot of yours?
Yes.
Because I want to see how...
We have a physical and a simulated, and they are exactly the same.
Okay. So
Or
you're
like-
down...
Cutting off about 10 hertz and about 3 kilohertz.
Okay. And you're already down -4.
Yeah. -4 on the sim. Yeah.
Yeah. Okay. Fantastic. And then let's go.
Yeah, after the 600.
Yeah.
That's fine.
Yeah, it's about half.
Yeah.
So it's it's what we'd expect. But the way that the milestone was set up, we tried to implement it that way. It didn't work out. But we do have some simulated results to show that we did implement it in some capacity.
Good. And so this one's the LT Spice. That's simulation, and that's what.
And that's what
Yeah, that's right.
So let's do it.
So when you were testing milestone 3 components, right? Did you do, because you're doing first order and second order, which are cascaded, did you simulate or run them experimentally separately?
Yeah.
we simulated.
Yeah, so we have actually our proof of concepts. Is one of them is the first order, one of them is the second order.
Do you have the Bodhi plots?
Yes.
Um,
Both proof of concept. We have those Bodhi plots.
So this was for the second order.
Second order high pass.
And go up to the first order?
I think the first order's down.
Yes.
Alright. So you got 0 decibels here as your
As a first
right?
order, yeah.
And do you have an LT Spice simulation of your second order? So we can
Oh, yeah.
yeah.
That was in the proof of concept.
Oh, yeah.
Let me see your special achievement. That's a transformer.
And you're getting 0 decibels there.
Yes.
How would you integrate both of these without having the issue that you're facing right
So
There's-
yeah,
it's
with
a very-
with a third order bandpass filter, my guess would be to cascade them, but use a voltage follower in between,
What
or
is
some
that
form
circuit?
of active separation. Yeah. Like an active filter of some kind to make it run the way we actually want it to run.
You're missing the buffer.
The
Yeah.
buffer. There you go. That's what I was not
Yeah.
voltage follower.
Yeah.
Buffer.
Yeah. Right? So one thing to note there would be your voltage follower is missing. And why would we need that voltage follower?
a voltage follower would keep the 0 decibels that we want
Isolate
and isolate
your
the two different
first
filters.
order and your second order.
So
your first order filter's output won't be affected by your second orders to a degree.
okay.
Because right now they're actually all combining. Those impedances are combining, so to speak.
Oh,
So if you,
okay.
so that's part of why you're right. That
We're
voltage
entering
power,
S domain.
which
Yeah.
what would have made you go, oh, is the filter design lecture on Monday, which I did not get.
That was, you couldn't
Because-
implement it at the last possible
So,
second.
There's as you design your filters, multiple orders. Every time you put in a filter, you need a voltage follower to keep them isolated.
Okay.
So
Yeah.
you have
Good to
learned.
know.
You have learned. It's not a negative. You did everything that we
Okay.
wanted to see, except that one thing.
Set us up.
Right? Yeah, we did.
This
And
will all be-
that's what failure. This is a good failure.
It's like the light
This
bulb
is
is
this will
going
all
on.
be this will all be included in our manual.
And yes, it will.
Yeah.
And in the future, be like, I remember when we did this third order filter, but didn't put buffers in. Like, you'll actually remember it.
Oh yeah.
Versus if I told you.
Oh yeah.
So it's still good. You're good. I like
Too
the
many
fact that you
hours were
figured it
put
out.
into this.
Yeah, I'm glad you figured it out in this way.
Yeah.
Yeah.
Far too much of that with these
Right,
battery
you did it
cables.
by yourself, like you figured out the Miller integration.
Yeah, that is
by yourself.
I probably
with a really good explanation.
I did the proof of concept for that one, and I remember like just sitting in my room trying to make an integrator. Like, why isn't a capacitor and resistor working? I need some other resistance
Right.
in the loop.
So you did this. You're halfway to the right answer for
Yes,
this,
exactly,
which is
exactly.
beautiful because I can talk out my face forever. And be like, yeah, and it goes out the door like within an hour. But now you got it. You got it for life. All right.
Exactly.
So, I only need, let's see, what else I need. Do you have any calculations of what you expected for your filters? Did you try it? It's got to be in your program.
Yeah.
Yeah.
The
Yeah,
cutoff
so-
frequencies are.
Yeah, so pretty much we picked around 10-ish for the low frequency cutoff.
Okay.
And then I just picked whatever components we had in our parts kit, and then left X to be a resistor.
Yeah.
Then it came around 2200,
Okay.
so I was like, okay, I'll throw 2200 in, and
Yeah.
then 10.7 is close enough to 10,
Yep.
which was our goal.
Yep.
Good.
So you did really think about the components you had, back calculate, and very correctly, it's easier to find a different resistor than to find a different conductor.
And then I think Joe did it.
And I did the low pass filter, which then cut off. I think it was like 3.7. I can't read, or 3.1 hertz.
Okay.
3.1 kilohertz.
Kilohertz.
Because the motor was protected up to 4 kilohertz, designed to operate around 2 kilohertz. Or like that's exactly what we want.
Cool. All right. As far as all the main things, did you calculate something? Did you simulate something? Did you probe a simulation somewhere? I still want to see you probe a live one too.
Yeah.
I mean, it's a little extra, but I do want to see it. And then, did you probe anything in your circuit? That's the other thing. So let's see. What do I want to see?
Yeah, there's-
What do I want to see?
I can show you the two things we probed the most,
Okay,
which were the.
Yeah, the PWM.
I showed you. I think I showed you one, which is the output of mouse
Yeah, you
one.
did. You did. Yes, sir.
So do you want to see PWM now?
Yeah, let me see
Okay.
the PWM real quick.
Okay.
Can I see it with the light on it?
Yeah, 1 second. That is the wrong one.
There's only 2 questions there. Okay.
Let me know when you want to plug that in.
Okay, that's good. I'm just trying to find the correct one. Here it is.
So many drivers.
Another thing we learned was you should get one of those
The
small wire kits.
The low wire breadboarding kits.
Yeah.
Because all of these jumper cables are absolutely mess.
It's a whole thing.
Oh, we use for testing.
Often those cables are near value.
So like,
Really?
I think 90% of them diagnosis circuit is cables.
What?
That's hard to
Plugged in,
define
right?
for TA's nightmare.
Something is
yes.
not plugged in. What's this? Something has been disconnected. I'm not sure
Which
what.
happens with the mess of wires. I'll wait a minute.
Okay. going on here?
If it doesn't connect, hopefully we can get it to connect. But our PWM signal is around
Why is that?
700-ish hertz, and we found that the astable multivibrator didn't actually change time cycle with the way we set it up. It actually changed time off.
Yeah.
So it in turn changed frequency, which we had to. Yeah, we had to change a bunch of different aspects of the circuit to get that to work, but we were able to integrate that.
That's one of my questions. Your answers.
Okay.
Okay, what's going on? Why is this is not?
Because the professor asked for
Uh,
what happens in research? Sometimes we can. Oh no.
It's not working.
oh wait, someone unplugged.
Someone. I didn't do it.
Not me.
Not it.
You have a question from your picker?
Wave jet. Okay, that's wave
There
gen
we
one.
go.
Oh, that's still not it.
Oh, okay.
Still not plugged in right. Okay. Wave gen 1 goes there. Scope 1. Okay, and then there we go.
Perfect. PWM signal that we want.
So you adjusted the PWM.
Yeah, you can adjust PWM based on where the light is.
Okay.
And yeah, it doesn't actually adjust time on. It only adjusts time off, but it does end up working with the specs of the motor.
Oh.
Like, I see it.
Okay.
We're good. Perfect. Very close. So you're awesome. You did that.
Huh?
Very nice.
What is it actually doing?
So we can change how fast the motor goes by where the light is.
The paper fall off?
Yeah, the paper fell off. You gotta put the paper on. They're doing the a proof of concept prototype-ish of a sunflower. This is the sun.
Oh, I see.
Yeah.
So it's following the sun's opinion.
Yeah.
Yeah.
So for extra points, you really should have a little flower, you know.
Sorry. They technically have solar panels and all that thing.
Here. This is a better way of just demonstrating it.
I got one Mr.
This was a bit finicky.
Yep. So,
Cool.
Okay. I think we're all good.
got it.
Is there anything else that we needed?
think, can you talk about any design choices at all that? Yeah, we did.
I was gonna say, oh yeah, we could talk about every design choice.
There's one that you did, and I was like, yep, that probably would happen. Which is any design choice that was beyond the content of circuits.
Miller integrators, astable multivibrators, and
There was another one that you didn't use. You didn't use the transistor.
the transistor. Yeah.
Yeah. Did you try like?
Yes.
So,
Oh yes.
It didn't work.
Okay, cool. And so internal electronics, if you take it later, you'll solve that. Like you go, oh, that's 100%. Right? Because you'll have to figure out what was the main issue again with the transistor. You remember? What kept making you go, this isn't.
I would say it was current drop. I can't remember.
Okay.
It was like never actually turning on, I think.
Okay, so you couldn't get it like to switch on.
Yeah.
It wasn't switching, which was the point of the transistor.
Yeah, so it wasn't switching. So
Yeah.
something about what the amount of current that's, and maybe also current and voltage together. So you're gonna look at eventually the IV curve,
Oh, okay.
and then understand where you were on the IV curve. And that's what you don't know yet.
Yeah.
Which is a little bit more complicated than what we do.
Yeah.
So you'll go, oh, okay, yeah. When you get to that, okay, great. So this one I have to write down for you.
Okay. This was a bit long, so I'll have to upload it to YouTube. But
That's fine.
long to stop recording?
You can stop it, yeah.
Okay.
That's all I want to know. Good job.